Welcome back to MATA35. In the second half of lecture today, we're going to be talking about applications of eigenvalues and eigenvectors. Unfortunately, in order to do that, we're going to have to first spend a little bit more time in math land before we can go back to biology land, where you can apply all these facts about linear algebra and eigenvalues and eigenvectors to understanding how a population grows as time goes on. So, how do we interpret these eigenvectors and eigenvalues? So if we have n distinct eigenpairs, we can interpret the action of A by what it does to each of the eigenvectors. Just a moment, let me... So, for example, wait, where was I? Oh, there. Okay. So, for example, if we have a 2 by 2 matrix, let's say A is equal to 3, minus 1, minus 1, 3. I'm not going to make you solve them right now, but you all know how to solve for eigenvalues and eigenvectors now. It turns out you have two eigenvalues. Lambda 1 is equal to 2, lambda 2 is equal to 4. And you have v1 is equal to 1, 1, and v2 is equal to 1 minus 1. And of course, you can scale these eigenvectors by multiplying, and they're still eigenvectors. So what does this look like? Well, if you're thinking about shapes, what this means is that you have your eigenvectors. So this is your 1, 1 eigenvector, and this is your 1 minus 1 eigenvector. And when you're scaling it, this eigenvector gets doubled, and this eigenvector gets multiplied by 4. So if you started out with some circle, let's say you started out with a circle here, what this is going to do is this is going to scale it out into this big oval. So we can still understand this transformation because we have this different set of axes where we can, instead of using the normal axes, you can sort of see the scaling on a different set of axes as you by using the eigenvectors as your axes instead of your original axes. So if x is equal to, if some vector, if you can write it as a linear combination of eigenvectors. So actually, let me use slightly different notation. Let's call this, what do I use later? I think I use C's. Some constant times v1 plus some constant times v2. Then ax, by the distributive property, is going to be equal to a times a c1 v1 plus c2 times a times v2. So ax is going to be equal to a times lambda 1 v1 plus, oh, sorry, that's not an a. That's a c. c1 lambda 1 v1 plus c2 lambda 2 v2. Because it's just scaling each of the axes, each of these eigenvectors independently, and then you can add them back together. So now, this gets us to the idea of a basis. So remember, we said in the last lecture that the standard basis of Rn is E1 through En, where each Ei is a vector with all zeros except for 1 in the ith entry. And any vector can be written as a linear combination of EIs. So let me just write this out. So R3, so this is the set of three-dimensional Euclidean space. So you have E1 is equal to 1, 0, 0, E2 is equal to 0, 1, 0, and E3 is equal to 0, 0, 1. And of course, for any vector x, y, and z, you can write this as x times 1, 0, 0 plus y times 0, 1, 0 plus z times 0, 0, 1. Now this might seem a little bit silly, and it is a little bit silly, but what this just means is that you can write everything as some linear combination of your E1s, your E2s, and E3s. So some multiple times those added together. But now you might ask, the whole point of a basis is that you can write any vector as a linear combination. Are there other sets of basis vectors? And the answer to that is yes. In fact, there are, well, infinitely many, as is often the case in math. And so if you have any set of n vectors such that you can write every vector as a linear combination of them, then that is called a basis of Rn. And it turns out that if you have any linearly independent set of n vectors in Rn, that you have a basis. So a set of vectors, remember that the set of vectors is linearly independent if none of the vectors can be written as a linear combination of the other vectors. Let's go ahead and give an example. So let's suppose that we had a set of vectors 1, 1, and a set of vectors and 1, minus 1. So recall these were the eigenvectors of our matrix that we were looking at earlier. So this is a basis. It's a different basis, but it's still a basis of R2. And we can check this. So now, suppose that we had one of these you could write as a linear combination of the others. So that's C times 1 minus 1. Well, then 1 is equal to C is equal to minus 1, which is a contradiction. And so because this is a contradiction, 1, 1 and 1 minus 1 are linearly independent. So note that this is a basis, and you can, in fact, you can write out any vector x, y as some combination of these. And this is going to be a little bit more complicated, but this is going to be x plus y times 1, 1 plus x minus y over 2 times 1 minus 1. So for example, a vector 2, 4, you can write as a linear combination 3 times 1, 1 minus 1 times minus 1. Okay, so basically these are alternate axes you can think of these as. So they're not always necessarily orthogonal or not necessarily perpendicular, but these are alternate axes that you can use to write any vector, alternate set of coordinates. It's an alternate coordinate system to write vectors in your space. Now why does this matter? This matters because sometimes you can write a basis out of eigenvectors. So if you have n linearly independent eigenvectors, those eigenvectors form an eigenbasis. Let's give an example. So, could I slow down a bit overall? Yes, I can. So sorry about that, Sam. So we have 3 minus 1 minus 1, 3. So we already know the two different eigenvectors, and we just showed that they were linearly independent. So this has an eigenbasis 1, 1, 1, minus 1. On the other hand, 1, 1, 0, 1, if you compute the eigenvectors of this, you'll find that this has only one linearly independent eigenvector, 1, 0, so no eigenbasis. So note that eigenvectors corresponding to different eigenvalues are always linearly independent. So if you have different eigenvalues, then you know that their eigenvectors are linearly independent. And let me give a quick proof of this. You don't need to understand why this is true, but you do need to know that this is true. So if you have AV1 is equal to lambda 1 V1 and AV2 equal to lambda 2 V2, suppose that you can write one as a multiple of the other. V1 is equal to C1 V2. Then AV1 is equal to C1 AV2, just multiplying both sides by A. Which then implies that lambda 1 V1 is equal to C1 lambda 2 V2, which implies that lambda 1 C1 V2 is equal to lambda 2 C2 V2, which implies that lambda, I just messed that up. Let me fix that. Okay, so we just multiply both sides by A, and when we multiply that out, you get lambda 1 V1 is equal to C1 lambda 2 V2. But we know that V1 is equal to C1 V2. So this implies that lambda 1 C1 V2 is equal to lambda 2 C1 V2. And so these parts cancel out, so this implies that lambda 1 is equal to lambda 2. And so if the two eigenvectors are linearly dependent, then they have to be correspond to the same eigenvalue. So another thing you can do is you can find all linearly independent eigenvectors corresponding to an eigenvalue by setting each of the free variables after a Gaussian elimination. So in the previous case, at the end of our solving the system of equations, we only had one free variable. But sometimes you end up having two. And let me give an example of that. Let's suppose you had 2, 0, 0, 0, 2, 0, 0, 0, 1, x, y, z is equal to 2x, 2y, 2z. So when you solve the system of equations, what you have is 2x is equal to 2x, 2y is equal to 2y, and z is equal to 2z. So this implies that z is equal to 0, because otherwise z can't be equal to 2z. And so you're left with two free variables, x and y. And so your vector v is equal to x, y, 0. And you get two different eigenvectors. And so these are actually linearly independent eigenvectors. So linearly independent. So basically, once you do your solve for your equations, usually when you solve for eigenvectors, you only have one variable at the end. If you have more than one variable at the end, then that means that you actually have two different linearly independent eigenvectors, and you can plug in one of the variables equal to 1 and all the others equal to 0, and then the other variable equal to 1 and all the others equal to 0. Or whatever they're equal to. So let's try this out, and I promise after this next slide, we'll be back in biology land. So let's try it out. Do you have an eigenbasis for each of the following? Let me reset. Oh wait, what happened to my... Oh no, okay, that's still working. So let's reset. And, oh, I need to give you the actual matrices. So, do you have an eigenbasis? Yes, no, maybe, question mark, none of the above. Maybe. Okay, well, I mean, maybe isn't wrong, but... Okay, it looks like I went too fast, because it looks like people are confused. Okay, so this is why I have this chat. This is why I have this in place. So we have a couple A's, mostly B's, C's, and D's. Okay, so it turns out that the answer to this is actually yes. And the reason for this is we have two distinct eigenvalues, 1 and 2. And this is a 2 by 2 matrix. And you also have two distinct eigenvectors, which are 1, 0, and 0, 1. But you didn't have to actually compute that. And so the answer to this is actually yes. Okay, let's try another one. Let's try this one here. And let me reset. Okay, so now a lot of people think that the answer is no because there aren't two distinct eigenvalues. But unfortunately, this is one of those cases where if there are distinct eigenvalues, then you have distinct eigenvectors. But just because you don't have distinct eigenvalues doesn't mean you don't have distinct eigenvectors. And so the answer to this is also yes. And let's write this out. So yes, because if you solve for this matrix, what you end up with is 1, 0, 0, 1, xy is equal to xy. Since you have one eigenvalue and you're solving for that, so x is equal to x and y is equal to y. So two free variables. Yeah, so if you have two free variables, then you end up with two different things. So v can be equal to any vector xy, and so you get an eigenbasis 1, 0, where you set x is equal to 1, y equal to 0, and 0, 1, where you set x is equal to 0 and y is equal to 1. Yep. So if at the end you end up having two values, that means that two free variables, that means you can get two linearly independent eigenvectors out of it. Okay, so let's try again. So I have 2, 1, 0, 2. So let me reset again. Does this have two linearly independent eigenvectors? So do you have an eigenbasis? Let's see. Okay, so we have some A's, we have some B's. Okay, well, let's see what happens. So note that we have 2, 1, 0, 2 xy is going to be equal to 2x, 2y, right? Let me separate these out. Right? And so because of that, what we have is we have, if you solve the system of equations, you have 2x plus y is equal to 2x, and 2y is equal to 2y. So this means we don't have any constraints on y, actually. But when you put these together, you find that that implies that... oh, actually, sorry, you do have a constraint on y from the top one. So that implies that y is equal to 0, and no constraint on x. And so v is going to be equal to x0, which implies you just have one eigenvector, and so the answer is no. Okay, let's try one last one. So, 1, 1, 1, 1. You've seen this matrix before. So, does this have an eigenbasis? And let me reset before you guys answer this. Okay, so we're getting a lot of no's, and we're getting let's see, do we have a few yeses? So let's try solving this and see what happens. So 1 minus lambda and 1, 1, 1 minus lambda. Because we want to compute the eigenvectors, eigenvalues, right? So what are the eigenvalues? So the eigenvalues are 1 minus lambda squared minus 1 is equal to 0. So you get lambda squared minus 2 lambda is equal to 0. And lambda times lambda minus 2 is equal to 0. Lambda equals 0, 2 distinct eigenvectors. And therefore, the answer is actually yes. Because you have 2 distinct eigenvalues, and therefore you have 2 distinct eigenvectors as well. Okay, so that was not that great of a hit rate. Okay, so tell you what, we are going to, so I had planned on finishing up eigenvalues and eigenvectors today, because I thought we'd got through all the material. We're going to do more of it on Friday. So you guys should ask your TAs about this in class in tutorial Wednesday, Thursday, and we're going to practice this, and I'm going to try to give a completely different explanation of it on Friday, just to try to get you guys to make sense of it. No, that's quite all right. Like, one of the things as a teacher is if everyone is confused, then that means it's my fault. So this is my problem, not your problem. But it does mean that it is something we should solve together, and so Friday we'll spend more time on eigenvalues and eigenvectors. But I did promise you we're going to go back into biology land. So let's end today's Wednesday class by going back into biology land and seeing how this all applies to biology before going back into math land again a little bit more on Friday to make sure we all understand what these eigenvectors and eigenvalues actually mean. Okay. So, it turns out that if you have a Leslie matrix for a population, so for population growth rates, and you have eigenvectors v1 through vn with eigenvalues lambda 1 through lambda n, if the initial population vector, if you can write the initial population vector as a linear combination of your eigenvectors, then the population after t time periods is just going to be a1 times lambda 1 to the t times v1 all the way through an lambda n to the t times vn. And the proof of this is actually relatively straightforward, so I'm going to write it out, and then we're going to apply this. So the proof of this is just, well, the population vector after t time periods is g to the t. I don't know why I use g here. I think I was using using L everywhere else, but using different variable for the Leslie matrix. So it's g to the t p, right? So then this is equal to g to the t times a1 v1 plus dot 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 plus an vn, because that's what p is equal to. And so this is, you can use the distributive property. This is a1 g to the t v1 plus dot 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 plus an g to the t vn. But note that g times vi is going to be equal to lambda vi. So when you have g to the t vi, you're just doing that t times, so that's lambda I to the t vi. And therefore, this is equal to a1 lambda 1 to the t v1 plus dot 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 plus an lambda n to the t vn. Okay, so now that we've done that, let's go ahead and see how we can apply this to biology. So suppose we have an age-structured population for birds where you've divided up the group into young and old birds. Each old bird has one hatchling each year, so one young each year, but always survives. So we're assuming that the old birds never die. However, each young has 1.5 new hatchlings, but survives only half the time to the next year. So if you start out with 2 young birds and 1 old bird, what is the population after 10 years? So now, in order to do this, we need to write out, so P0 is going to be young and old, which is going to be equal to 2, 1 to start off with, right? And we have a Leslie matrix, so from a young bird, you're going to get 1.5 new young birds and 0.5 old birds. And the old birds are going to give you 1 young bird each year, and it's going to remain alive, and so you're going to get 1 old bird. So now the first thing we want to do is we want to compute the eigenvalues. So what are the eigenvalues? So you compute that by 1.5, by 1.5 minus lambda 1, 0.5, 1 minus lambda. So this is going to be equal to 1.5 minus 2.5 lambda plus lambda squared minus 0.5 is equal to 0. And when you solve this is a little bit ugly to solve, but when you solve this, you get lambda minus 2, and lambda minus 0.5 is equal to 0, and lambda is equal to 2 or 0.5. So we have 2 eigenvalues, and so now we want to solve for the eigenvectors. So note that because we have 2 eigenvalues, and because this is a 2 by 2 matrix, this means we do have an eigenbasis. We just need to solve for this eigenbasis. So you end up with lambda 1 is equal to 2, and you end up with 1.5, 1, 0.5, 1 times xy is equal to 2x, 2y. When you solve this, you end up just getting a single an equation 0.5x plus y is equal to 2y. And when you solve this, you'll find that x is equal to 2y, and v1 is going to be equal to 2, 1. Lambda 2 is equal to 0.5. You do the same thing, so 1.5, 1, 0.5, 1 times xy is going to be equal to 0.5x, 0.5y. And that turns out, after solving this, it's going to give you x is equal to minus y. And so v2 is going to be equal to minus 1, 1. Question, if we have 2 eigenvalues for a non-2 by 2 matrix, do we still know that there are 2 eigenvectors? So if you have 2 eigenvalues, then you always know that there are 2 linearly independent eigenvectors. But of course, if it's a 2 by 2 matrix, that's also an eigenbasis. If it's a 3 by 3 matrix, 2 eigenvectors isn't enough because to form a basis, you need 3 of them. So here, note that P0, 2, 1 is one of our eigenvectors. So that means that P10 after 10 years is going to be equal to 2, 1 times 2 to the 10, which is going to be equal to 2048 over and 1024. And this is because we knew the sort of eigenvalue scaling behavior. Because our original population was one of our eigenvectors, we could just scale it up 10 times and just multiply by 2, instead of having to do the matrix multiplication 10 times in a row. And this is sort of the power of these eigenvectors and eigenvalues. And we can also do it for a slightly more complicated example. So using that same example, if we have an initial population of 3, 0, so 3 young and 0 adults, you can write this as a linear combination I think I was actually using C, so let me keep on using C. You can write this as a linear combination of the two eigenvectors. And when we do this, you need to solve for C1 and C2. You end up getting C1 is equal to 1 and C2 is equal to minus 1. And therefore, you know that 3, 0 is equal to 2, 1 minus 1, 1. Okay, so that shouldn't be too hard to figure out that this is true. You can just verify it. So then P10 would be equal to 2 to the 10 times 2, 1 minus 0.5 to the 10 times minus 1, 1, which is equal to 2048, 1024, minus 1 over 1024, 1 over 1024, which is about equal to 2048 over 1024. So one of the things you might notice is that the behavior seems to be completely dominated at long timescales by the largest eigenvalue. And this turns out to be something that's generally true and allows us to understand these sorts of populations as time goes to infinity. So once you let the population run for a very long time, the eigenvectors tell you what the population is going to be close to. And I think that's where I'm going to end today. I will cover this all again on Friday, since it seemed like we still had some misunderstandings. So we'll cover this all again on Friday in the next lecture. So I will see you on Friday.